Everyone, my name is Ishmin Kaur and I'm 16 years old. For the past 2 years, in my freshman and sophomore years of high school, I've been learning AI and I've become pretty good at it. But I realized that AI is not useful unless you apply it to some domain. And one thing I've been interested in, other than AI and technology, is finance. When I was 9 years old, my dad was trying to get me to trade stocks with him and he was teaching me the ways of the stock market. Once I looked deeper into finance, I realized that finance is way more than just the stock market, and it left me interested. So I decided that this is going to be the domain I'm going to apply my AI skills to. So I started this Coursera course on Columbia's financial engineering, and I'll put the link in the description for what that was. And when I looked at it, it looked so complex in the first module. They were testing our math skills, and I've never acquired those math skills before. So I looked at prerequisites, and even the prerequisites require me to have knowledge of calculus 2, calculus 3, linear algebra, stochastic probability, and I just didn't know enough of that. I've taken most AP stats in my school, and I've taken calculus 1. So I decided to learn calculus 2 or calculus BC. And through this, I hope to learn more math like linear algebra, calculus 3, and then I can finally start my prerequisites for this course, and then I can finally start my financial engineering course. So in this video, I'm going to go through what I learned in Calculus BC. I'm not going to go through all the concepts. I'm just going to go through one thing, which is proving Euler's identity, but that builds up upon a lot of Calculus 1 and Calculus 2 topics. And if you want to see the corresponding article, you can just look at my Medium link in my bio, and that'll lead you to all my articles. I'm not going to go over every single concept in calculus, but one topic I found really important was Euler's identity. And this identity is e to the I times pi plus 1 is equal to 0. And you're probably wondering, how did we even get here? E is some constant, 2.7 blah blah blah, and I is the square root of -1, and pi is 3.1415, and it goes on and on for infinity. How do these concepts connect? And how does adding 1 to this make it 0? Because that would mean that e to the I times pi is equal to -1 if we subtract -1 on both sides. Well, today I'm going to prove it, and I'm going to teach concepts along the way so that you can understand how this identity works. Let me first start with the topic local linearization. Let's say I have some function f of x, and the graph of f of x looks something like this. So this is my x-axis, this is my y-axis, and then it looks something like this. And let's say we want to find a way to approximate, we don't know what this function is, but we want to find a way to approximate what the value of the function is right here. So I don't know what this function is, but I do know one thing. I know what the value of this function is at this point, and I know what its derivative is at this point. So let's call this point A. I know f of A, and I know the derivative of f at A. And let's say I want to approximate this point over here. It's close to A. What I can do is I can create a linear approximation of this function at this point, and it'll give me a tangent line like this. So then I can approximate what this point would be using this tangent line because I don't know what this function is. And I can do that by creating a line with f of a and f prime of a. And that is y equals f of a plus f prime of a times x minus a. So let me test this out with a real example. Let's use the function f of x equals x cubed. And I'm going to use this function to prove that this formula actually works. So let's say that we're going to prove it we're going to use a is equal to 1. So then f of a is the same thing as f of 1, which is 1 cubed, and that is equal to 1. Pretty simple. Now we also need the derivative of this function, and we need to evaluate it at a too. So f prime of x, well, let's use power rule. This 3 comes out in the front, and we decrement the powers by 1. So then we get 3x squared. Now we evaluate the derivative at a, which is the same thing as evaluating it at 1, which is 3 times 1 squared, which is equivalent to 3. So now we have our information. We have f of a and we have f prime of a. Now we can plug it into the function. Y equals f of a, which is 1, plus f prime of a, which is 3, times x minus a, which is 1. Now, why is this function actually useful? Let's say we weren't given that f of x equals x cubed, but we knew what f of a was and what f prime of a was. Well, then what we can do, we can approximate points that are pretty close to a without needing the function. So let's say I want to evaluate it at x equals 0.9. That's pretty close to this function over here, this value over here. So then I just plug that in for x. 1 plus 3 times 0.9 minus 1. If you plug this into a calculator, you get 0.7. And let's say that we wanted to check how accurate this value is. Let's actually evaluate x to the third power at 0.9. So 0.9 to the third power, if we put it into our calculator, we get 0.729. And that's pretty close to 0.7. So we can use local linearization to approximate points that are close to our a. So if we choose a equals 1, we should use values that are close to a that we want to approximate. So I wouldn't use this line to approximate what maybe -5 is. If we plug in -5 here, what we'd get is y equals 1 plus 3 times -5 minus 1, which is equal to 1, plus 3 times -6, which is -17. And if we do -5 to the third power, well, that's -125. These two values are not close at all. So we should only use linear localization if we are close to our a, if our x is close to our a. So local linearization allows us to approximate functions, but it's not that accurate. How can we make it more accurate? Well, let me reinforce the idea that you use this formula, which is y equals f of a plus f prime of a times x minus a. What if we take the derivative of this equation? Well, this is a constant, so it zeroes out. And then we have let me expand this, f prime of a times x minus f prime of a times a. Well, f prime of a just times a, that's still a constant, so this would zero out. And all we're left with is the derivative of f prime of a times x. Well, that's just f prime of a, because we're treating f prime of a as a constant. So if that's the only thing left, then we can see that in this function, the derivative of our local linearization is equivalent to the derivative of our actual function. So what if we made it so that our approximation also has our second derivative equal to the actual second derivative of our function, and then the third derivative to be equivalent to the actual third derivative of our function also, and this keeps on going until infinity? That would help us create a really good approximation. It would probably be exactly what our function is. And this is what a Taylor series does. It assumes that we have a function that has infinite derivatives at some point a. And for many functions, if we know the derivatives at this point, we can reconstruct the original function using the Taylor series. So what is a Taylor series? So the Taylor series states that if we have some function f of x, if we take the derivative starting at n equals 0 up until infinity, our function to approximate is the sum of that derivative at a divided by n factorial times x minus a to the n power. But why does this even make sense? To show you the intuition for the Taylor series, I'm going to show you the first 4 terms of it. So let's say n equals 0. And our abstract function f of x, I'm not going to define it. I'm just going to leave it as f of x plugged in f of a. So at n equals 0, we have the 0th derivative of f of x at a, which is just the function f of x. So that's f of a divided by 0 factorial, which is equal to 1, times x minus a to the 0th power, which is just 1. So the first term of our approximation, I'm going to call it y, is f of a. How about at n equals 1? Well, that's the first derivative at a divided by 1 factorial times x minus a to the first power. So 1 factorial is just 1. So this is just, we're going to add f prime of a times x minus a. Now, our next one is the second derivative of a, n equals 2, divided by 2 factorial, which is just 2, times x minus a squared. So our next is f to the second derivative times x minus a squared divided by 2. And let's do our last term. Well, that's going to be, I'm going to do it up here. And at n equals 3, that's the third derivative at a, divided by 3 factorial, which is 3 times 2 times 1, which is 6. And that times x minus a to the third. So now we have our first four terms. I'm just going to bring this one here. So the third derivative at a times x minus a to the third divided by 6. For simplicity, I wrote the formula up here and I defined it as g of x. So let's say I'm going to center this Taylor series at a equals 0. And the special case is this Taylor series where you center it at a equals 0. This is called the Maclaurin series. So now I'm going to plug in 0 for a. So I'll have f of 0 plus f prime of 0 times x, because this becomes a 0, and then plus f prime prime of 0 divided by 2 times x squared. And then the third derivative evaluated at 0 divided by 6, and this is just x cubed. This looks a little bit simpler because I centered it at 0, and it'll help me get my point across a little bit better. So let's say I evaluate this at g of 0. Well, because there are x's on each of these terms, it multiplies everything by 0 for that term. So this term zeroes out, this term zeroes out, and this term zeroes out. And all we're left with is f of 0. So now our approximation, g of x, is equivalent to the function f of x at a equals 0. So that's a good sign because it gives us a pretty good approximation. Now, if we take the derivative of g of x, we get, well, this is a constant. F of 0 is a constant, so it zeroes out. And we're left with f prime of 0 plus, well, now let's treat this f prime of 0 over 2 as a constant. So then we just use power rule. This 2 comes in the front, and then this is decremented by 1. So then 2 times f prime of 0 divided by 2, well, these 2's cancel out. So then we just get the second derivative at 0 times x. And for this one, we treat this as a constant. This 3 comes in the front, and if we multiply that, that cancels out, so we get f third derivative evaluated at 0 divided by 2. And then that times, we decremented this 3, we get x squared. So now if I evaluate the derivative of g at 0, these terms zero out, and I'm left with f prime of 0. So the approximation is equivalent at our function f of x at the point 0, and it's also, its derivatives are equivalent. Our original function f of x, the derivative, and the derivative of g of x. Now for the second derivative, if we evaluate, this is the second derivative, I already evaluated it, it's pretty repetitive, so I decided not to show it again. If I evaluate this at 0, I get the second derivative. And if I take the derivative of g again, I will get g, the third one, is equal to this. So the third derivative is also equivalent. So doing this until infinity will get us our best approximation. So now that you understand the fundamentals, I can finally start proving this identity. Let's start by taking the Maclaurin series, which is just a Taylor series at a equals 0 for the functions sine of x, cosine x, and e to the x. So let's start with e to the x. It's a pretty simple one. So we have f of x is equal to e to the x. So what is the value of this function at a? So at a, which is 0, e to the 0 is just 1. Now what is f prime of x? So the beautiful thing about e to x is that its derivative is just going to be itself. So at 0, the derivative is also equal to 1. And because we're just taking the derivative and we just keep on getting e to the x, all the derivatives are actually going to be 1. So if we plug it into the Taylor series formula, we are going to get something like this. So I'm just going to move this down here, and e to the x is equivalent to, well, our first term is just going to be f of 0, which is 1, plus f prime of 0, which is 1, times x, plus f, the second derivative of 0, which is 1, times x squared divided by 2 factorial. See, n and n, they both are n, plus the third derivative at 0, which is 1 again, times x to the third, and then 3 factorial, and then let's write another term, 1 times x to the 4 times 4 factorial. I think you're seeing a pattern now, and this goes on until infinity. So that was a pretty simple explanation for the Maclaurin series of e to the x. Let's move on to sine and cosine, which are a little bit more complex, that need a little bit more thinking, but it's still pretty simple. So now let's do the Maclaurin series for sine of x. And I just put the formula and I just put a as 0 for the Maclaurin series. So you can keep it in mind as we are forming our series. So let's start with the first term. So f of x is equal to sine of x. So at 0, sine of 0 is equal to 0. That makes sense. Now let's move on to f prime of x. Well, the derivative of sine of x is cosine of x. And f prime of 0 is cosine of 0. And cosine of 0 is just equal to 1. Sorry, that kind of looks like theta. I'm just going to change that to a 0. Okay, now let's take the second derivative. The derivative of cosine of x is negative sine of x. And negative sine of x, if we evaluate that at 0, negative sine of 0, well, sine of 0 is just 0, so this will be 0. Let's take the third derivative. Well, the derivative of sine of x, that would be cosine of x, but there's a negative, so it's negative cosine of x. And if we evaluate that at 0, we get negative cosine of 0, which is, well, cosine of 0 is 1, so this would be negative 1. Now let's take the fourth derivative. It's getting kind of repetitive because now we're back to sine of x, because the derivative of cosine of x is negative sine of x, but there's a negative, so it goes back to positive. Well, now we just know that the fourth derivative is actually the same thing as the value of the function, which is 0. So we get this pattern, 0, 1, 0, negative 1. Now let's write this as our approximation. So sine of x is equivalent to, well, the value of the function is 0, so the first term is not even there. The second term would be 1 times x divided by 1 factorial, so that's just x. So that's just x. And then for our next term, well, the derivative is 0, so we have no next term. So then we have to go to the third derivative, which is actually just a negative. So this is negative x to the third, because it's the third derivative, divided by 3 factorial. And this is negative because the third derivative is negative 1. And this pattern repeats, so x to the 5 factorial minus x to the 7 factorial, and so on. And this has this plus and minus repeating pattern. Let's do the Maclaurin series for cosine of x. So f of x equals cosine of x. Evaluate that at 0. That is equal to cosine of 0, which is 1. I'm going to do this pretty fast so that we can get to the point, because it's pretty similar to sine of x. So the derivative of cosine of x, well, that would be negative sine of x. So if we evaluate that at 0, we would get negative sine of 0. Sine of 0 is just 0, so this is 0. The second derivative of sine of x, that's cosine of x, but this is going to be negative because there's a negative out in front. So if we evaluate that at 0, that is negative cosine of 0. Cosine of 0 is 1, so there's going to be negative 1. The third derivative, well, the derivative of cosine is negative sine. Since we have a negative, that turns it into a positive. So then evaluate this at 0. We know sine of 0 is just 0. And then, similar to sine of x, if we take the fourth derivative, well, the derivative of sine of x is cosine of x. And this is the same thing as our original function. So the fourth derivative will be 1. If we evaluate it at 0, of course. So now we can construct our pattern in a similar way as we did with sine of x. So cosine of x equals, well, we take the 0th derivative, which is the function itself, so that was 1, times x to the 0, which is just 0, over 1 factorial. So we can just write this as 1. And then our next term, Well, f prime of 0 is 0. So our next term is zeroed out. We don't have a next term. The third term is the second derivative. So the second derivative evaluated at 0 is negative 1. So we have negative 1 times x, well, n is 2. So x squared divided by 2 factorial. And then our third term, like the first term, not our third term, our fourth term, like the second term, our third derivative is just 0. So our fourth term will not exist. So it'll just be zeroed out. And then we move on to our fifth term, which is the fourth derivative. Well, cosine of x is just 1. So we have plus 1. And since n is 4, we're going to go n to the fourth, x to the fourth, divide by 4 factorial. So that means this pattern is going to repeat. So it's going to be x to the 6 factorial, plus x to the 8 factorial. And we have this alternating plus and minus, just like we did with sine of x. So now we have our 3 functions, and we define them as Maclaurin series. So for e to x, since all the derivatives are 1, it's kind of in this nice pattern where it's just x and then x squared divided by 2 factorial, x to the third divided by 3 factorial, and it's a pretty simple pattern. For sine of x, we start at x, and then we have all the odd powers. We have all the odd ones. And then the plus and minus alternate. And similarly, so does cosine, but for even powers. So x second, x to the fourth, x to the 0. And it kind of looks like if we add sine and cosine, we get something that's similar to e to x, but not really, because we would get 1 plus x, which is how e to the x starts, but then we get minus x to the second divided by 2 factorial, minus x to the third divided by 3 factorial. And over here, it's positive, as you can see. So we don't get a perfect match. So how can we express e to the x in terms of sine of x and cosine of x? So we can't really express e to the x in terms of cosine of x and sine of x, our Maclaurin series of them, but we can represent it with e to the I times x. And in this case, I equals the square root of negative 1. And from algebra 2, you probably know that I squared would be negative 1, I to the third would be negative I to the fourth would bring us back to 1, and this pattern would repeat. So we know that the Maclaurin series of e to the x is 1 plus x squared divided by 2 factorial plus x to the third divided by 3 factorial. And this pattern kind of repeats until infinity. So what if instead of having x, we plugged in ix? Then it would look something like this. So this is what happens when we plug in ix for each x. So as you can see, there's probably a way to simplify this. And we can do that using what I wrote down over here. So to simplify it, well, 1 can't be simplified, and ix can't be simplified. But ix squared can be, because this is equivalent to I squared times x squared. We know I squared is just negative 1. So then the I is gone, and we have x squared divided by 2 factorial. Now I to the third times x to the third. Well, this is a negative I, so we have negative I, x to the third divided by 3 factorial. And this pattern will repeat. So since we have I to the fourth times x to the fourth, I to the fourth is just 1. So that's x to the fourth divided by 4 factorial, not 5 factorial. And then we have I to the fifth times x to the fifth, I to the fifth, that is just I. And then we have x to the fifth divided by 5 factorial. This kind of looks like we're getting nowhere, but what if we separate our imaginary terms and our normal terms? So then, if we want just our normal terms, that would be 1 minus x squared 2 factorial plus x fourth 4 factorial minus x 6 factorial. And we're going to do the same. So anything with I, we're going to take out the I, and we're going to get x minus x third 3 factorial plus x to the fifth 5 factorial minus x to the seventh 7 factorial. So this section repeats until infinity, and so does this one. So if we look at this section carefully, we realize that it is the Maclaurin series for cosine of x. Then for this one, if we look at this part, this is just the Maclaurin series for sine of x, and we're just multiplying it by I. Now we're getting pretty close to the definition of our identity. So e to the ix is equal to cosine of x plus I times sine of x. Now that we got our formula using the Maclaurin series of e to the x, cosine of x, and sine of x, now we can finally get close to our identity. So let's evaluate this equation over here. We're going to evaluate it with the value x is equal to pi. So now that's where we get our e to the power of I times pi. And we have to evaluate cosine of pi, and then I times sine of pi. Well, cosine of pi, that would just be equal to -1. And then sine of pi is just 0. So this term is canceled out. So we get e to the power of I times pi is equal to -1. If we add 1 to both sides, we get e times to the power of I times pi plus 1, that is equal to 0. Now, we finally reached our conclusion of Euler's identity. So now, in my personal journey, my next steps is that I'm learning linear algebra. And linear algebra is a completely different world than calculus from what I've seen so far. And when I'm done with linear algebra, I'm also going to make a similar video to this to document my journey and maybe help some people who want to learn more about math. See you in the next video.